Our site is located in Aberdeen on the southern coast of Hong Kong, home to one of the last remaining urban marine villages. A fishing community continues to live aboard boats, surrounded by stagnant water, poor circulation, and increasing pollution. Environmental analysis revealed strong southern sunlight and southeast winds funneling across the harbour basin. Using pathfinding and tidal simulations, we explored new boat routes and zoning strategies. This led us to one key intervention, the fish market, where the disconnect between city and sea is most visible. The existing market is shaded, damp, and overcrowded, with chaotic circulation among workers, tourists, and vehicles. It lacks ventilation and spatial coherence. This raised a fundamental question: how can we redesign the fish market to support ecological responsiveness and community cohabitation? Rather than impose a fixed modular layout, we proposed a spatial system shaped by movement, access, and tidal flow, generating dynamic zoning through simulation-based logic. The design combines three systems: a tidal-responsive floating platform, a solar water adaptive roof system, and a biotensile membrane transformed by salt and time. The platform design begins with a simulation of water currents across the site. We used particle flow to map how water moves through different functional zones, then generated geometry directly from the flow trails. This created a porous floating surface that supports intertidal activity and underwater growth. The roof plan responds to the form of the platform, while the tensile curtain follows the drainage logic of the roof. We detailed the platform with stands for fish sorting and selling, where fishermen can place, clean, and display their catch. Floor grooves were mapped using shortest path logic to return water back to the ocean. Below, a structural stand allows the platform to rest on poles at low tide and float at high tide, maintaining adaptability and stability. To support a self-sustaining community, we explored what the site itself could provide. Waste materials like shells, fish skin, algae, salt water, and discarded nets became inputs for responsive building components. We tested biopolymer mixtures using agar, gelatin, chitosan, and calcium carbonate. Hand extrusion helped assess flexibility and bonding. The composite was poured onto different fabrics. Microscopic imaging confirmed calcium carbonate crystallization, stabilizing the mesh as a biofabric. To scale up, we added shell aggregates. This led to stronger crystal formations and stiffer material surfaces. Shrinkage tests showed stability with slight curvature. Salt crystallization tests in indoor and outdoor conditions showed better results outdoors, where faster evaporation encouraged denser growth. These material behaviors allow architecture to grow from site waste and react to its surrounding climate. The roof system extends our material research through responsive biofabric tiles. Each tile is made from chitosan, calcium carbonate, and salt, softening under rainfall and adjusting its slope based on moisture. To understand light response, we trained a model on algae morphology under varying sunlight. These patterns shaped how tiles bend or flatten, generating daily shifts in curvature across the roof. Tension simulations guided where to place seashell aggregates, reinforcing areas with low stress to enhance stability. As curvature accumulates, the roof's geometry becomes more complex, passively shading the space below. Deeper curves block light, while flatter zones remain open. Rainwater simulation shaped the overall form, dividing the roof into 3 drying zones. Each directs flow to targeted areas, informing the layout of the timber structure beneath, which supports and follows these paths. The tensile membrane is shaped by water paths from the roof. Anchoring points are placed where rain flow slows down the most, forming a responsive tension structure. 2 crystallization processes occur over time. Salt grows from tidal movement below. Calcium carbonate forms from rain above. Together, the project operates as a metabolic system. Its parts are not fixed, but constantly reorganized by use, weather, and tide. Structures shift, crystallize, or dissolve, depending on environmental input. Zones can expand, decay, or reform without replacing the whole. The design shows a living framework that absorbs waste, responds to climate, and supports seasonal or social transformation over time. We introduced a tidal-based zoning system where programs shift with water levels. At high tide, elevated areas support fish processing and docking. At low tide, new platforms emerge for markets and gathering. A system of floating bridges adapts to water levels, reconnecting zones while allowing continuous access for people and boats. In section, the system reveals its layered logic. Platforms rise and fall around fixed poles, while roof structures trace the same environmental flows, blurring the line between infrastructure and ecology.